Right, hello and welcome, folks. We are on to Chapter 2, and I am just super excited to be out of Chapter 1. If you've been paying attention to these videos, I've told you Chapter 1 is my least favorite chapter in the book. I think it gets so much better in Chapter 2, and Chapter 3 has been better than Chapter 2, and then it just keeps building from there. So sometimes people tell me, I didn't feel like I liked geometry at the beginning of the year. I liked it at the end of the year, and I think that is a great thing, and I hope that I make that happen for you if you didn't really dig Chapter 1 all that much. But anyways, we're jumping into Chapter 2. I can make these videos a bit shorter now, I think, because, it's going to start flowing, because now you know something, right? Chapter 1, you didn't know anything, right? You had to start from the very, very basics and get it all built from there. But now, because you know stuff, right? That's kind of how we approach it here, is we want you to get some stuff in front of you so that you know it, so that you can actually do stuff with it, rather than just be stuck figuring it out on your own, right? So hopefully you feel like you know something at least, and that's going to serve you well in Chapter 2, and then you're going to do more interesting stuff this chapter, I think, and I hope it will be engaging, and you'll learn this stuff very, very solidly. Anyways, you're looking at it here. You probably already read it already. We had here parallel lines and planes. That's the name of Chapter 2, and I start with this up top, right above me here. I wanted to really, really highlight this, because even though Chapter 2 is better than Chapter 1, Section 2.1, it's not that interesting of a section. And the reason for this is because we're going into parallel lines and planes, right? We see this in the middle of the screen here. We're going into studying something very specific. From now on, the chapters are going to be pretty specific, the things that it's going to look at. And if we're looking at something specific, like parallel lines, then remember, we're going to be building towards further and further knowledge throughout the chapter about parallel lines. So if we're going to build towards deeper and deeper knowledge, what's the thing we probably need to start with? Because remember, in geometry, knowledge comes in three forms. They come in definitions, which are human created, right? Just described. It tells you what the thing is very simply. And then you have postulates that are agreed to, which are rules, right? Assumptions about those things that we want to make that we can't prove. And finally, there are facts, right, that follow from our original assumptions and definitions. So that being said, what's the first thing we're going to have to do this chapter if we're going to spend a whole chapter looking at relationships and things that happen when you have parallel lines? Well, you guessed it, or maybe you didn't guess it, it's right above me here. You're going to do definitions today, okay? So whenever we have definitions, it's just not as interesting of a class, because again, it's just about getting stuff out there, knowing what it is, so then you can do stuff with it in future chapters. So parallel lines and planes, we got our picture here. I'm going to throw a little bit in the book here that you see here today. Again, get excited. New chapter begins today. We see in front of us, looks like these kind of rows. Looks like rows of corn or something like that. You plant them in lines that are parallel, right? You know parallel. In Algebra 1, you study parallel lines. The slopes of parallel lines need to be the same. We don't have to worry about that yet, at least. Not until Chapter 11, where we look at parallel slopes and perpendicular slopes. But parallel hasn't even been defined for you yet here in geometry. So you have parallel lines here. You got some parallel lines right here. Oh, and then you have this other line that's not related to these lines here. Or maybe it is related, okay? So this line here that's crossing these many parallel lines, it's actually something called a transversal. So the book kind of talks about that at the beginning, and we'll define what a transversal is for you today. It says here, the rows of crops showed in the photograph and the strips of earth between them suggest parallel lines lying in the plane, right? So when we have parallel lines lying in a plane, we can say a lot of things about relationships that happen when we drop, say, for instance, a transversal. It says the roads cutting across the rows suggest transversals. So when we have parallel lines cut by another line, right? A transversal is just kind of another line that goes through two or more lines and intersects it in more than in one place on each line, one distinct place on each line. Anyways, we'll get to the definition later. In fact, transversals don't even have to be for parallel lines. They could be non-parallel lines. We'll get to it all later. But if they are parallel lines, interesting things happen when we have a transversal like this road cutting through all these parallel lines. We can say stuff about angles. We definitely can say stuff about angles, and that's going to get us to further proofs later on in the book. Okie dokie, so that is your introductory slide. We got definitions today, because those will build to some assumptions we'll make, and very few assumptions. It'll be mostly theorems and proofs, and getting those facts out there. Sections 2.2 and beyond. That's the stuff that I'm really looking forward to in Chapter 2. But we can get through this today, and I think we can get through this today fairly quickly compared to Chapter 2. So let's get started on it now, guys. I'm just like my country, I'm young, scrappy, and hungry, and I'm not throwing away my shot. We gonna rise. Alrighty, right. We got here section 2.1 definition. Dive into it. write it down right away, guys. Let's make this quick. Let's see if we can keep this under a half hour. No promises here. Definition. We got definition of parallel lines. So parallel lines are coplanar lines that do not intersect. All right, parallel lines. So I know there are a lot of things you can say for describing parallel lines. Observations you've made in the past in Algebra 1 maybe about what a parallel line is. You know when you see them, but this is how you word it out. This is as simply as possible what makes for two lines that are parallel to one another, or parallel lines. So again, with just like perpendicular, you had a symbol, you have a symbol for is parallel to. So this symbol means is parallel to. Or you can abbreviate parallel lines by just dropping in these side-by-side tick marks, kind of long lines, right, to indicate just small two parallel lines. But this symbol, again, stands for is parallel to, just like the perpendicular symbol stands for is perpendicular to. But anyways, the two criteria. Okay, so here, if you're looking at diving into this definition, you got two criteria. The two lines got to be coplanar. And the second thing is that they can't intersect. Okay, so if you're picturing the cube, and we'll look at the cube in a second, you have lines that are coplanar and non-coplanar. So if it's parallel lines, you got to just be thinking of the coplanar lines now. Okay, so here we just drop it down. This isn't a cube, right? If we picture a cube right here, like this line here, and it's like a line like this on the side of a cube here, those would not actually be coplanar lines. But here this looks, maybe it's the top of a cube or something like that, but this is a plane here, so they're coplanar. They don't intersect, so this would meet the definition of parallel lines. These ones here would also meet the definition of parallel lines here, because if you just have two lines drawn on a sheet of paper or on a computer screen and shown to you, that's suggesting that these figures here are planar figures, right? They exist on a plane. So the plane can be drawn out, or it could just be written down on a piece of paper, and that you take it as a given. These are coplanar lines, and they appear to be parallel. We don't know for sure. If it didn't say given that H is parallel to K, then you're looking for these check marks here. Okay, so these little arrows here, this heading this direction, this heading this direction, they're usually in red in the textbook, but obviously if you're on pens and pencils, it doesn't have to be a specific color or anything like that. This would indicate that H is parallel to K. Okay, so remember this symbol stands for is parallel to. H is parallel to K. All right, so we got one definition written down. Again, I talked for a while there. That buys you time to write it down and think. Do you have any questions? Do you get it? Where's this going to, too, by the way? Okay, so I talked about parallel lines. We've talked about perpendicular lines. We're not really care about that today. We've also talked about intersecting lines in the past. So perhaps let's think about maybe another type of line we haven't really talked about yet. Parallel lines are coplanar lines that do not intersect. Intersecting lines they're coplanar lines as well that do intersect, and they intersect in exactly one point, as we know from the last section. That would be a theorem that was actually proven, that I talked through the proof of it. So this is the final situation. This is another definition you need to know about how two lines can relate to one another. Okay, so again, lines can be parallel to one another. Lines can be intersecting, right? There are actually three relationships here. Lines can be parallel to one another. They can be intersecting, right? And that includes being perpendicular to. That's just a specific type of intersecting lines. And thirdly, two lines in our three-dimensional world, right? Two lines in our three-dimensional world could have this relationship up here. Look at this here. Notice this here. Do these two lines intersect? No, they don't. Based on the way this is drawn, this intersection is drawn, they do not intersect. We have a line here, and then this dashed line means it's kind of behind this line over here. Okay, so these two lines do not intersect, but they don't fit the definition of parallel lines. So we will not call these lines parallel to one another. Why not? Why not? Well, obviously, they're not coplanar. Okay, so this is a situation where we have non-coplanar lines that do not intersect, and they're going to get a different definition here. So go ahead and write this one down. This is the definition of skew lines. These lines are skew from one another. Skew kind of means like skew a certain direction, move away from one another, right? So skew lines are like two ships passing in the night, right? They don't really come that close to one another. It's like a point here is kind of close to that point, but they just skew away from one another, right? They don't touch one another. They're just like away, rather than like parallel lines are like always the same distance from one another. And we'll prove that actually, that parallel lines in every point is equidistant from the other line, right? From its corresponding line that would actually be at a perpendicular from the other line here. Okay, so skew lines, write that one down. That's an easy definition to forget, but it's also a very easy definition to master here. These are non-coplanar lines that do not intersect. And they look kind of crazy like this here, right? You're not used to drawing lines like that. Okay, so let's show it in here for a second. So we got maybe we're talking EH right here. That's a line, okay? This is coplanar with FG, all right? So these would be parallel lines right here. So that would be an example of skew. But this would be skew if I had line BG, right? That would be skew. These are not parallel because they're not coplanar. We could run a plane like this that includes that line. We could also run a plane diagonally like this that includes this line, but that's not going to capture this line right here. So this line here, this diagonal line down here, I could draw on FB, right? FB would be another line skew to this line. Think, is there another line you can think of that would be skew to EH in this diagram? Think for a second. This is line EH. What's another line in this diagram that's skewed to EH? Did you say GC? Yeah, GC is also skew to EH. So one thing that I want to point out too, another thing that your book actually, so normally books definitions, right? You want to have them be as simple as possible just to point out something, and then you can prove stuff beyond that. And I was just thinking about this year. It's the first year I really thought about this, but skew lines, it says, are non-coplanar lines that do not intersect. And I put down here that a more simple way that this could be defined, right? That skew lines could be defined would simply be non-coplanar lines, right? So you don't even actually, for skew lines, you don't even actually need to mention the part that they do not intersect, because if you have non-coplanar lines, what do you know about those lines? Well, any intersecting line, okay, let's say here, any intersecting line is going to, any two intersecting lines are going to be what, right? Any two intersecting lines are coplanar, right? Are coplanar. We knew that in section 1.9, right? So for instance, EF and EA, right, are consumed or included in this EFB, right? That is a plane or whatever. So there's at least one plane, or exactly one plane, that contains any two intersecting lines. Okay, so by theorem, any two lines that intersect will be coplanar. So any two non-coplanar lines means that they would not have been able to intersect, right? Would not have been able to intersect, and therefore they would be skew, right? They would be skew from one another because they'd be non-coplanar and not intersecting. So anyways, that's just one thing that I thought about there, is that if you can't run a plane to include both of the lines here, then obviously it's not parallel, because parallel lines need to be coplanar, and it's not intersecting because intersecting lines also need to be coplanar, as we learned in section 1.9. So skew lines, even though it's defined like this, non-coplanar and non-intersecting, non-coplanar would be enough information to determine that the lines were actually skew, would fit the definition. So something to point out there to get there. Anywho, so this title of the chapter is Parallel Lines and Planes. So we haven't talked about parallel planes yet, but we'll talk about those now. First thing I want to call out is that planes are never skew. Okay, so thinking about parallel lines, how many situations do you have for parallel lines? If you have two, or just lines in general, how can two lines relate to one another? Well, obviously one is that they can be parallel to one another. We see that written up here. So lines can be parallel to another, and what are the other two ways that two lines can relate to one another? Two lines could be intersecting, or two lines can be skew. Okay, two lines can be skew. So planes can never be skew. So that means that planes can either be intersecting, or what else can they be? They can be parallel to one another. Right? It can be parallel to one another. So obviously here, looking at this diagram right here, either they're going to be parallel planes, like plane X and plane Y are parallel to each other, as suggested by this diagram, if this is a right prism here. X and Y are parallel to each other, but planes can't be skew, right? If we tilted X a little bit, right, in any direction, we tilted it backwards this way, tilted it in any direction, it'll eventually intersect with plane Y, because these planes are infinitely thin and infinitely wide, right? And infinitely tall, right? So in 2 dimensions goes forever and ever, right? Goes all the way this way, all the way that way, and this way and this way, right? So if we tilted them at all, they're going to intersect. So you can't have skewness, right, when it comes to planes. Right? There's no way to draw 2 planes. And remember, skewness has to do with being coplanar or non-coplanar. If you're talking about planes, you don't really care about coplanar or non-coplanar. It's just, do they intersect or do they not intersect? And then if they don't intersect, the definition is parallel planes. Okay, so here's another definition here. 2 planes that do not intersect are called parallel planes. Yeah, parallel planes. And this can be indicated just by using the same is parallel to symbol. So this symbol means is parallel to. So plane EHD, for instance. So I already talked about plane X parallel to plane Y. It appears here, if this were a right prism, then we could conclude that plane EHD is parallel to plane FBC, for instance, right? These 2 lateral sides here, lateral surfaces here of this prism are parallel to another. So we have 2 parallel planes here. Okay, quick reminder on this, the reason why I write this out here. So a plane might be labeled with 1 letter, might be named 1 letter, like this is plane X, this is plane Y. If your plane is not labeled with a particular specific letter, then the way you can name them is you can just choose 3 points that are on the plane, specifically 3 non-collinear points, right? Non-collinear points, okay? Because through any 3 non-collinear points, there is exactly 1 plane that can be defined. That's, again, a reminder of one of the takeaways from section 1.9, which you just did. Okay, so we talked about lines, right? Lines can relate together 3 ways. They could be parallel, they could be intersecting, they could be skew. You need to know the definitions for all 3. Planes relate to one another by either intersecting, you know about those, non-intersecting, which means that they're parallel planes, so you know those definitions. The thing we haven't talked about yet are how lines and planes could particularly be classified with one another. And this is a final definition here for this introduction kind of to this chapter here. It says here a line and a plane are parallel if they do not intersect. Okay, so the only way that we're going to talk about lines and planes together is whether they intersect. And right, this is being an example of a line that intersects with this plane because the plane contains the whole line. Or if we drew a line that just pierced through the plane, it intersects the plane in at least 1 point, right? Because it could be 1 point or it could be all the points. Line could intersect a plane if it pierced through it. But a line could also, like we had a line up here, for instance, like parallel to this line here up here, then this line would be parallel to the plane. Okay, so this is a definition of a line can be parallel to a plane. This is pretty self-explanatory definition. If you look at this diagram right here, like line ED, which again, I chose one of the harder ones, the diagonal this here. Draw that through. So it's coming this way at us through the screen here infinitely, and then going through the screen, going that way infinitely. This line would be parallel to plane FBC, this one over here. So this line, because it's on this parallel plane, right? Because it's on a plane parallel to this plane, it's not going to ever touch this plane over here. So that's sometimes this will be given to you once or twice in a theorem that you got to prove. So just be prepared for it, right? A line can be parallel to a plane. So another example would be line FG would be parallel to plane Y. Okay, because it would always be above Y, never intersect Y. Okay, so more definitions here. So those are just the definitions about how lines relate to one another, planes relate to one another, and line and plane relate to one another. So know all of them. 3 ways for lines, those 2 ways for planes relate to one another, and the 2 ways that a line and a plane, right? A line can either intersect a plane or it can be parallel to a plane, and know those definitions. Okay, so the big thing for this chapter is talking about transversals. So we need to define those right now for you guys here. Notice here in the diagram, first thing to jump out here, this is a common mistake because I think you probably say, hey, Mr. Ford, I already know this. Why are you wasting my time? I learned this in middle school. No, I think a lot of you guys make mistakes with this when I go through this with you guys the first time through and talking about transversals, because look at this diagram right here, guys. Look at this. So one of these is a transversal. This is named line T is technically a transversal. I'll go through the definition in a second. But one thing I want to point out, are any of these lines parallel to one another? Are any of these lines parallel to one another? No. None of these lines are parallel to one another. So transversals, the definition for transversal is not written for a situation where you have parallel lines. H and K could be parallel to one another, right? It could be given to you that H and K are parallel to one another. Great, this would still be transversal, but transversals have to do when you have two lines, okay? Two lines crossed by a third line. Two lines crossed by a third line in two distinct points. That's the definition, and let's get this written down here, okay? So a transversal is a line that intersects two or more coplanar lines in different points, okay? So that was a good thing that I didn't say a second ago. I basically told you the definition, but I forgot to say coplanar. So, you know, obviously you could have skew lines that are touched by, so for instance, EA is skewed to FG, and like line AF, right? Line AF would touch both of those lines, but that would not be considered a transversal, because EA and FG are non-coplanar. Anyways, so this is sort of the most general that they could draw a diagram like this. A transversal is a line that intersects two or more coplanar lines in different points. So this being said, which is what's the transversal we're talking about here in this diagram? So obviously, all these lines are going to intersect at some point, but given to us in the diagram where we see clearly, we're going to talk about this is the transversal in this diagram. It's got to be line T, okay, line T. So think about it for a second. Line T, that's a transversal because it intersects these two lines in different points, right? Intersects the line here and a line K here, H here and K there. So line T is a transversal of lines H and K, okay? How many transversals do H and K have, right? How many different transversals could we draw in for H and K? Yeah, infinitely many, right? Infinitely many. We could draw a transversal like this, draw a transversal like this, draw a transversal like this. So different transversals will show you different things and tell you different things, okay? And if H and K are parallel to one another, there's going to be a lot more things we can include, which we'll get to in the next section, okay? Today is just about getting used to transversals, getting used to the ideas of some of the vocabularies here. I underlined this here just as a quick aside, just to point out to you that, remember, every definition comes from where? Comes from the what? The three undefined terms, okay? So just want to point this out, that the kind of important language here, other than saying like numbers like to or is or that or different, right? So sort of the basic English that we have here. Any other words we use in a definition come originally from the undefined terms. So again, a line was an undefined term, which we started geometry with. Intersects, we talked about that being shared points between planes, lines, and points. That came up in the first section of the book. And then coplanar lines, right? That's a description of lines that was defined for us when we talked about two lines that could exist in the same plane. And then finally, points, another undefined term. Okay, so sometimes it's easier to remember a definition or write it down by like thinking about what undefined terms are kind of stacked together to get us to a definition. So a transversal is a line that intersects two or more coplanar lines, right? Got to be coplanar in different points. And that's what we have here. Okay, so one thing you got to know about this here, right? This might be abbreviated for us here. T is a transversal of H and K. I'm going to move on. One thing you got to know is something called interior angles, right? So you're probably wondering or probably thinking, right? Like we have a transversal here, right? Transversal intersects two or more lines. And for this diagram, there are just two here. And why is everything numbered, right? Why is everything numbered? Well, if this transversal intersects two lines, how many angles get created? Oh, 8 total, right? Because two lines intersecting form 4 angles, right? 4 angles up here, 4 angles right here. So you have these things, and if these lines were actually parallel, you'd have some angle relationships. Like, how could 6 relate to 2? How could 4 relate to 8? Look, 4 and 8 are both obtuse. 7 and 3 are both acute. Interesting. 1 and 5 are both obtuse. So anyways, we want to talk about some of the relationships here. So we're going to classify these angles. These 8 angles could get classified some various ways. So you got to know those here. First, we could be talking about the interior. So here, this is like one of the main diagrams you're going to deal with this year in geometry. 2 lines cut by a transversal. You'll be seeing that all the time very, very soon. But 2 lines cut by a transversal. There's an interior of this situation, okay? So if we think about what could possibly be an interior rather than exterior, well, that's what's inside, right? Inside the two lines, right, that are getting cut by the transversal. Transversal has nothing to do with interior, exterior, right, because the transversal is not paired up with anything. So H is paired up with K, so this is the interior of what's going on here. Angles 3, 4, 5, and 6 are interior angles. And exterior angles, right, those are just going to be outside of the two non-transversal lines in this series of two lines cut by a transversal. So angles 1 and 2 and 7 and 8, those are going to be your exterior angles. And that'll be important. We talk about that next section as well, and proving stuff when we have parallel lines here. Okie dokie. Let's do it here because there's more. Make sure you got this. Make sure you got the understanding there. Maybe label it up real quick. Interior angles, exterior angles here, right? Labeled. Do you have it labeled? Okay, we're going to look at it another way. So maybe draw this diagram yet again. Draw it again. Or I'm drawing it a little differently this time, right? I'm drawing it a little differently this time. So in addition to exterior and interior, angles are classified by the side of the transversal. Okay, so when we say side, when we're talking about side in this situation, right, we talk about exterior of the two lines, interior of the two lines. That's the way we talk about the two lines that are cut by the transversal. If we say side, we're talking side of the transversal. So here's the right side, here's the left side. And we're not going to say left, we're not going to say right. We're going to classify angles by being on the same side, or we're going to classify them by being on alternate sides. Okay, so same side, alternate sides. Same side, alternate sides. 2 and 5 are alternate angles, right? Alternate angles of some kinds, right? Of some kinds. We'd have to come up with more words of that. Between like 2 and 7, for instance, that's a different type of alternate angles. 3 and 6 are a very specific kind of alternate angles. 6 and 2 are one type of same side angles. 6 and 4 are a different type of same side angles. And that's all stuff we'll have to talk about today. Same side interior angles. Yes. So same side angles here. So 6 and 2 are not same side interior angles. In fact, they're not even same side exterior angles because 6 is not an exterior angle. 4 and 6 are both. So the interior angles are these 4. So if we're just talking about the interior angles, then 4 and 6 would be same side interior angles. 3 and 5 would be same side interior angles. And that should allow you to think about what we're talking about next in terms of interior angles. Interior angles could either be same side or they could be alternating. So our alternating interior angles is stuff you're going to talk about a lot. So I'll have theorems for sure about alternate interior angles. Get that down. Get same side interior angles down and get alternate interior angles down. Really want to highlight this. Okay, so what are the alternate interior angle pairs? Okay, so 4 and 6 are same. We're talking angle pairs again, right? Like these things come in pairs here in geometry. 4 and 6 are same side interior angles, and a pair in angle 3 and 5, another pair, corresponding pair of same side interior angles, and alternate interior angles. So we're going to talk 3 and 6 here because these are just supplementary to one another, right? These are supplementary to one another. So that means we're talking alternate interior angles here are 3 and 6 and 4 and 5. Make sure you write that down. Corresponding angles is the next one. Okay, so we've just talked about the interior angles here. Not really going to talk about the exterior angles, but you could probably get the idea of what alternate exterior angles are, right? Like 2 and 7, 1 and 8. What we need to talk about now is when you have interior angles and an exterior angle. So notice here, 6 and 8 are just supplementary. We're not going to classify those. Those are just supplementary angles because they form kind of two parts of a straight angle. So now we want to talk about, well, what if we have an interior angle here, and then we have kind of its same position in the other 4 angles that we have here? 6 and 2 are in the same position. Notice that here. That here we have an angle in the top right here, another angle in the top right here. One's an exterior angle, one's an interior angle, right? These that we want to talk about here, and what these are called corresponding angles. Okay, so figure out how you can take notes on that and label that and make that very clear. 6 and 2 are corresponding angles. Who can tell me another pair of corresponding angles? Ones that are in the same position. So corresponding means they just go with one another, right? They're kind of close to the same thing, right? They're close to the same place. 7 and 3, for instance, right? 7 and 3 are corresponding, right? We have this, even though this is an interior angle, this is an exterior angle, right? It's in the corresponding position in these, right? We got 1, 2, 3, 4, and we got 5, 6, 7, 8, and 8 and 4 go together. 7 and 3. I think hopefully you get the idea here that we have 4 pairs of corresponding angles, because every pair, when we have a transversal situation, every angle has a corresponding angle. Okay, so put some more words up here because we might reference this once or twice, not very much. But what do you think alternate exterior angles are? I already kind of talked about that a minute or two ago. What about same side exterior angles? Sure, you can also have same side exterior angles. Give me a pair of same side exterior angles. Yeah, angle 1 and angle 7, right? So that could be abbreviated same side exterior angles. Okay, so all these actually can be abbreviated. I wasn't planning on going this with you, but here's how you can abbreviate this. You might want to write this down really quickly because theorems will be abbreviated using this stuff here. We have same side. I usually do s-s, and then I do int angles. Same side interior angles is this here. So you can write that down super quickly, move on with your life here. Okay, alternate interior angles. Here's how you can abbreviate this. Alt, int, angles. Okay, angle symbol, put the s here. It means plural, more than one angle, right? Alternate interior angles, these are all pairs. So we'll have to have angles there. Alt, interior angles. Alt, int, angles. Okay, so write this down so we all kind of write it the same way and you know what I'm talking about when this comes up in the future. Corresponding angles, I usually do corr, just the first 4 letters, and then angles here, and we're good to go. Okay, so these are kind of what I've seen the most, but obviously you can abbreviate it different ways. But if we're all abbreviating it, these 3 situations just like this, then we're going to know what we're talking about with one letter, and that makes it a lot easier. These I'm not going to worry about because you're usually talking about same side interior angles, alternate interior angles, or corresponding angles. And that's how we have it abbreviated. Okie dokie, let's jump into some oral practice. Identify different pairs of angles. There we go. Corresponding angles, alternate interior angles, and finally same side interior angles. See if we can get all pairs of angles. Ready? Well, not ready, set, go. So I'm going to help you out. Oh, man, is Mr. Fortin being too nice to you right now? Maybe being too nice to you. Check it out here. Okay, so I dropped in just an example for each one. I gave you 1 pair as an example. What I want you to do is name all of the remaining pairs, okay? All the remaining pairs, all the remaining corresponding angles, alternate interior angles, and same side interior angles. Ready, set, go. Who can do it fastest? Who can do it fastest? Ready, set, go. Those corresponding angles, do it. The other corresponding angles. How many in total? How many pairs do you need? Just go. All right, write it down. What are the alternate interior angles? Pause the video if you need. I'm going to start maybe in about 20 seconds. We'll go. Those alternate interior angles. Get the same side interior angles after that. 10 seconds. 7, 6, 4, 2 seconds, 1, and we are done. Okay, hopefully that was enough time for you to get all the pairs. Maybe wrote it down, maybe you're ready to share with me, report to the clouds. But if not, just pause the video, make sure you get it, and then let's go over real quick. Okay, so corresponding angles. First of all, we have 1 and 3, okay? So we have 1 and 3 there. How many angle pairs are going to be corresponding here? Well, that's just 1 angle pair. How many more are there going to be? There are going to be 3 more, okay? So 4 angle pairs in total are corresponding angles because it's just what position it's in. So 1, so we can think about this as sort of top, right, bottom, left. Tops go together. Those are corresponding angles, 1 and 3. And look at this here. These are actually drawn kind of parallel. 1 and 3, those look like they might be congruent. 2 and 4 look congruent too. I don't know what's going on here. But anyways, I just said the other one, 2 and 4, 5 and 6. Oops, not 5 and 6, and 6 and 8. So you should have had 5 and 7 right here. So that is an error on the slide, but we just got it fixed. And that's that. Alternate interior angles. You're just gonna have 2 pairs of those. Angle 2, angle 7, angle 3, angle 6. Ooh, and look at these. Do these look alike? I think those look alike, quite a bit alike. Yes. And then finally, so the corresponding angles you need to know, alternate interior angles. So interior, remember the interior, these have got to be the 2 lines. This has to be the transversal here. Interior is here, right? Interior is here. So either you're going to be alternate or you can be same side. So we have 2 and 3 I've already told you about. 6 and 7 are the other same side interior angles, not exterior. You got to say that. You can't just say they're same side angles. They're same side interior angles. And that's that. Okie dokie. Man, we're about to wrap this up. One kind of random theorem now. Okay, a random theorem. We'll prove it briefly. I'm not crazy that this theorem's in here. I think it just comes up once or twice as you're proving other things. But again, this is just sort of an introductory section for a new chapter, chapter 2, which is much better. Okay, so our random theorem is going to have to do with parallel planes. Okay, so parallel planes. One thing we haven't talked about. So we just talked about two lines that maybe they were parallel, maybe they weren't. But they were cut by a transversal. So one thing that we haven't talked about is parallel planes that are getting cut by something. There's going to be something we're going to prove very shortly in a second with this here, okay? Parallel planes and something that cuts through parallel planes, similar to a transversal. Okay, so I know what you're thinking. Maybe you have some parallel planes. If I ran a line through two parallel planes, right, and it intersected the one plane here and another plane there. Just picture this in your heads. So you can definitely have a line that intersects both of the parallel planes, but there wouldn't be very much stuff we would need to prove with that, because we would know that that line would just intersect those two planes in one point and then another point. And there's nothing really we can prove involving just 2 points here. So what this theorem has to do with, it has to do with planes that are parallel to one another that are cut by a third plane. There is something that we can prove here if we have that particular situation. So we might as well prove it just so we have yet another fact in geometry that might come up later. Okay, so what might be able to cut through two parallel planes? Well, a line can go through two parallel planes. That's fine, but there's nothing we can prove with it. A plane going through two parallel planes. Remember, a plane that intersects another plane. What's the intersection of a plane and another plane? The intersection of a plane and another plane is a line. Okay, is a line. So if we have plane X here parallel to plane Y, and we have another plane, or any other plane that's non-parallel, right? That's not parallel to one plane. It's not going to be parallel to the other, right? It's going to intersect them both, right? Intersect them both here. Okay, so we have a plane parallel to another plane, and then we have a third plane that intersects those two, okay? What's the thing that we can prove here? What's the thing that you see that could actually be proven, okay? So remember what I said, right? If we had a line, so if we think about just the line here, so picture this is like a line right here. This would just intersect plane Y in this point and plane X in this point right here. And then there's nothing really we can prove about those 2 points here. We already know that they're collinear. There's nothing we can say. A plane, though, intersecting plane Y and plane X, they're parallel to each other. Remember, a plane that intersects another plane intersects it in a line, right? The line is a point, all the points in common of this plane Z and this plane X. And line M is the set of points that are in common between plane Y and plane Z. A plane intersects another plane in one line, exactly one line. And so what do you think we can prove here? What have I haven't said so far that you think you can conclude about this diagram? Again, we know that a line exists here. We know that a line exists here because it's two planes intersecting. What can we say? Is there something we can say about those two lines that hasn't been said yet, other than the fact that a plane intersects and creates those lines? The thing that we can say is that these two lines would have to be parallel to another. So that might be kind of obvious. You might be thinking, well, that's got to be obvious if they're, right, line L and line M are in parallel planes. They must be parallel to each other. That's great. You're almost there with your reasoning, almost there with your justification of this theorem. Let's just clean it up, make sure we say what we need to say in order to prove this theorem that I have up top here, okay? So, saying this theorem out loud, if two parallel planes are cut by a third plane, then the lines of intersection are parallel to each other. Simple as that, simple as that. So this is a provable theorem. Again, it seems obvious, but if you think with your givens and your proofs, let's think of the given statement here. If two parallel planes are cut by a third plane, right? So there you're given some information. You're given this, right? If two parallel planes, okay, so we have plane X is parallel to plane Y, and then cut by a third plane, and then plane Z cuts X and Y. Therefore, right, line L and line M are the points of intersection. Okay, so that's all given to us. We actually haven't said anything about the relationship between line L and line M, other than that they're lines, right? Other than that, we know that they're lines because of the postulate from section 1.9, in two planes intersecting. Okay, so this is why this is a theorem, is because in our if statement, it's not stated anywhere. It's not stated anywhere that line L would have to be parallel to line M. Okay, but this is very easily provable, and we'll go ahead and prove this right now. The lines of intersection are parallel to each other, so that means those lines of intersection, line L and line M, we're going to prove now that those two lines are parallel to one another. So let's go ahead and do that now. Statements, reasons are up there. Okay, so we'll start this very simply. Who's got my first reason? First reason is generally the easiest, unless we're trying to pick something out from the diagram. Okay, so don't look at the diagram because you can get what am I getting? Given. Yeah, thank you for jumping in there and telling me my givens. Okay, so I just listed everything out here. Line L is in plane X. Line M is in plane Y, so those are two lines, and plane X is parallel to plane Y. Okay, so I could have written that the intersections of those two are line L and line M, but it's already drawn. It's already kind of given to us up here. It's fine. So what we're going to do here is I got here step 2, line L and line M do not intersect. Also, too, as I go through this proof, don't worry about this one because, like, most of your proofs won't look like this. They'll be a lot, I think, easier and follow more patterns to it. We're just trying to show you kind of how some of the recent stuff can lead to proving things here. So, anyways, step 2, because of step 1, I can now say line L and line M do not intersect. Okay, why do I know that? Line L and line M do not intersect. Why would I know that based on step 1? Well, line L is in plane X, line M is in plane Y. What do I know about those two planes? Those two planes are parallel to one another. Okay, so this is the definition of parallel planes, right? Parallel planes. Because line plane X does not intersect plane Y by definition of parallel planes, then that means any points in those two planes will not intersect. So any line that's in plane X will not intersect a line that's in a parallel plane, right? It's through the definition of parallel planes. Okay, so now we know that line L and line M do not intersect. That's great. Question, why can't we conclude that L must be parallel to line M right now? Why have we not proven that yet? So I know that line L and M do not intersect, so that means they got to be parallel, right? Well, is there another way that two lines cannot intersect that's not parallel? That's right, those two lines could be skew, okay? Could be skew from one another. So what we need to prove in order to be parallel lines, so remember skew lines are non-coplanar lines that do not intersect. Here, right, we know that they don't intersect, but have we established that they're coplanar or not? No. Okay, so now we need to determine that they're coplanar. And how will we know that line L and M are coplanar? Well, I think we pretty clearly see it right here, and we see it in the diagram. Line L and line M, what other plane are they in? They're in plane Z. Okay, they're in plane Z. So that's given to us up top here. Plane Z contains those intersections of line L and line M. So therefore, that's a given to us. That's given to us up here. And now we can conclude that line L and M are what? They're coplanar. Okay, this step 3 is going to build to telling us that they're coplanars. This is the definition of being coplanar, right? Line L and line M are in the same plane. They're both in plane Z. So if they're contained by a single plane, if there's a single plane you can run through both lines, then they're coplanar. Okay, so now we got that the two lines are not intersecting and they're coplanar. So what's the reason we can get now to saying that those two lines are parallel to one another? And the reason for this is the definition of parallel lines here. Okay, so notice this here, right? This is one way you can establish. This is probably, you're not going to do this very often, but this is a way to actually prove this. If you had the other textbook, some of your friends last year might have had Mr. Sin. He teaches his white textbook. I've taught that one before too. But this is a way that you, in other geometry textbooks, oftentimes you do prove that lines are parallel to one another. You got to do that through definition of parallel lines. You prove that those two lines are coplanar and that they do not intersect. If they're coplanar, do not intersect, then it meets the definition of parallel lines, and we can say line L is parallel to line M. And there we go. We have a theorem here. Is this mind-blowing? No, this one's not. I think this is the last one where I really needed to get through, because the next section, you're going to get a whole bunch of stuff, but it'll be actually stuff that you use again and again and again. And with that, I think we're just about done with our introduction to geometry. I know I keep saying that, but we'll get there pretty soon where, hey, we can just start really grooving through stuff. And I think that really begins section 2.2 which is nice. I know I keep saying get done with chapter 1, but this was kind of another chapter, another section to kind of introduce stuff. Okie dokie, here's your homework. This is my recommended homework as of now. I know it looks like a lot of problems. You know, I get this slide a lot of times. People are like, oh no, like so much homework. No, this isn't much homework, okay? You got 12 problems for classroom exercises. You got 18 problems here. Don't spend any more than 1 minute on each problem. What does that mean? Are you spending exactly 1 minute on each problem? Because if you did, right, that's 18 problems, that's 12 problems, that's 30 minutes. Okay, that's 30 minutes max though, because some of these problems are just quick. Are these lines skew or not, right? You're gonna come up with the answer in like 5-10 seconds. Okay, so spend like 15 minutes on these, spend like 30 seconds a problem, no more than a minute. If you don't get it, right, we'll review together, I'll give you some help, and we'll have that 15 minutes of class or whatever it is to always go over homework. But you're doing these. You're coming in tomorrow, no more than a minute on each problem. You've thought about it, and then we get a chance to review, make sure you understand that. I circle these ones here, 31 to 37, because these should also be pretty quick. They might take around a minute at least for these. These are harder problems. Okay, so I circled these. You might be like, what's this talking about? You're gonna have to focus, right? Focus tomorrow and review these tomorrow. So these might be hard to do. And with that, we are into chapter 2, and looking forward to taking through this stuff, guys. Take care, and talk to you soon. Bye.
Facts are from my point of view. Facts don't do what I want them to. Facts just twist the truth around. Facts are living girl inside out. Facts are getting the best of them.